So in this chapter we're going to talk about thermodynamics. We touched on some of this in Chemistry 1, and we may have talked some about thermochemistry. But thermodynamics is the study of the laws that govern the energy and entropy changes of physical and chemical events. So like I said, energy we studied before. You did a little bit with that, and heat capacity and things like that in Chemistry 1. Entropy is something new, and we're going to talk about what entropy is here. So the first law of thermodynamics says that the energy of the universe is constant and can be transferred or transformed, but it cannot be created or destroyed. So this is known as the law of conservation of energy. So for example, I'll use an example. Let's suppose you have a cup of hot coffee that's sitting on your desk. Now, so the coffee is hotter than the surrounding air, right? So the coffee cools off. But that doesn't mean that energy is lost. That energy is not lost or destroyed somehow. It's basically simply flowing out of the coffee and into the surroundings, which is, in this case, the room. So energy can't be created or destroyed. And note also that it can be transferred or transformed. In other words, we can convert one type of energy into another. We can convert potential energy into kinetic energy or vice versa, but that energy is not created or destroyed. So all energy is possessed by an object is the sum of potential and kinetic energies. Okay. Now, potential energy, so for example, that is stored energy. Okay, so potential energy is stored energy. So it increases when you separate objects that attract. Okay, so for example, if you pick up a heavy book, or any heavy object and lift it, and let's say it's sitting on the floor and you lift it up and you're putting it on a shelf, you're increasing potential energy because you're separating objects that attract. In fact, you could calculate that if you knew the mass of the book and you knew the height that you lifted it, the distance between the floor and the shelf, we could calculate, and the force and the acceleration due to gravity, we could calculate that. We could calculate the amount by which the potential energy increased. So potential energy, like one more time, it's stored energy. And it increases when you separate objects that attract. So, for example, when you lift a heavy book, or if you have a couple of powerful magnets that are attracted to one another, and you pull those apart, that's increasing potential energy. Okay, and kinetic energy is simply energy of motion. Okay, the energy that an object has because of its motion. So, the energy that an object has is some combination of heat and work. Okay, or let's put it this way. If there's a change in energy, the change in energy appears as some combination of heat and work. Q is the symbol that we use for heat, and W is the symbol that we use for work. Okay, so the quantity of energy possessed by an object can never be measured or calculated. The absolute value. We can only measure changes in energy. So for example, back to my coffee analogy. You have a cup of coffee sitting on your desk. Even if we stick a thermometer in there and let's say we measure the temperature of the coffee and let's say it's, for example, 60 degrees Celsius, we still don't know how much energy the coffee has. Okay, even if we measure the mass of the coffee and we measure the temperature of the coffee, we still don't know how much energy the coffee has, because only changes in energy can be measured. Okay, so let's suppose that we know the mass of the coffee. Okay, and we said the initial temperature was, let's say, was 60 Celsius, and we cool it off and it cools down to 40 Celsius. Now we could measure the change in energy. So you might remember this from Chem 1, the heat capacity, change in heat or energy is due to the mass times the heat capacity times temperature change. If you know the mass of the coffee and the heat capacity of coffee, which would be, for all practical purposes, that would be the heat capacity of water, and we measure the temperature change, we could measure the amount by which the energy changed. But we still wouldn't know how much energy it started with. The same thing with my previous example. I was talking about potential energy and how if you have let's say you have a book, a heavy book that's sitting on the floor, and you lift it and you put it up on the top shelf of your bookcase, we could measure the change in energy. But we couldn't measure the absolute value, how much energy does the book have in any one moment in time. We can only measure changes. Same analogy, whether you're lifting a book or whether a cup of coffee is cooling off, that's changes in energy. So energy is a state function, meaning that it depends only upon the initial and final states and not the path taken between the two states. Okay, so the classic example is discharging a car battery. So let's suppose we have two identical batteries. Okay, and if we take one and we short it out, in other words, we just run one wire from one terminal to the other, which I would not suggest doing, but all the energy is released as heat. There's no work done. Okay. On the other hand, if we attach some wires to the battery and we use it to drive a motor, let's say to turn a fan blade and push air or to pump water uphill. Now we're doing work. We're at least, nothing is 100% efficient, but we're at least using at least some of the energy to do work. But the point is that in either case, the starting conditions and the final conditions are the same. You start with a charged battery and you finish with a discharged battery. And how much energy we get out of the battery does not depend upon how we take it out. We get the same energy out of the battery here as we do here. Okay, and that's what I mean when we say it depends only upon the initial and final state. So you have in between these two extremes, you would have an infinite number of possible pathways. Like I said, no motor is 100% efficient. Motor is going to get hot. Some of your energy is going to be used released as heat. Okay, so you could have 10% of your energy released as heat, or 20% or 30%. You might only use 90% to do the work, or 80 or 70. It depends on how efficient the motor is. But one more time, how much energy we can get out of the battery does not depend upon how we take it out. So we start with a charged battery, we finish with a discharged battery. So a spontaneous reaction is one that occurs with outside assistance, without us having to do anything to it, without having to put energy into it. Okay. So this says, however, nothing about how fast the reaction occurs. It could occur very quickly or very slowly. We can say that reactions usually go towards lower energy, which means exothermic reactions, and you should know what this means. It means that a heat reaction is giving off heat, are usually spontaneous. We could say that another way and say that probably a better way to say it is that a drive to lower energy is one of your potential driving forces for a reaction. But it's not the whole story, okay? There are endothermic reactions that happen. For example, boiling water, the evaporation of water requires energy. You're having to overcome the intermolecular forces of attraction between the water molecules, which in this case is hydrogen bonding. Okay, so if you have water sitting out, even at room temperature, just a pan of water, a beaker of water, a cup of water, whatever, if you leave it out long enough, it will slowly evaporate over time, even though the water never gets even remotely close to boiling. Okay. That's an endothermic process because it's basically taking in energy for that water to evaporate. Dissolving in potassium chloride. There's some salts, potassium chloride is just one example, that take in energy as the salt dissolves. Okay? In other words, the solution feels cold. It's like if solution's concentrated enough, it can be like you put it could be like you dropped an ice cube into the water. Okay, it gets colder because when something gets colder, that means it's taking in heat from the surroundings. Okay, so that's endothermic. Exothermic means your reaction is giving off heat. Endothermic means it's taking in heat. Okay, but the point is the sign. The enthalpy change alone cannot be used to predict the direction of a reaction. We can't say just because it's endothermic that the reaction won't happen, because there are endothermic reactions that happen spontaneously. And so why is this? Because in terms of driving forces for reactions, energy is only half the picture. Okay. There's another half of the picture that we haven't talked about yet, and that's entropy. All right. So what is entropy? It's the thermodynamic quantity that describes the randomness of a system. So in a word, entropy is randomness, or basically disorder. Okay. Now, S is the symbol that we use for entropy. Now, I've said this before, any kind of change, right? Temperature, entropy, moles of gas, it's always final minus initial. Okay, it's always final minus initial, right? So if we think of our reaction as going from reactants to products, right, then the reactions or the reactants are the initial state, and the products are the final state. So by saying final minus initial, we're basically saying products minus reactants. So the entropy of the products minus the entropy of the reactants. Okay. So it's important that you set this up correctly, due to otherwise you'll have problems with sign conventions, and you'll wind up adding something instead of subtracting it. Sometimes it's supposed to come out negative. So if delta S is positive, the products have more entropy than the reactants. Okay, and if delta S is negative, the products have less entropy than the reactants. So qualitatively, we can look at this, and by looking at a reaction, predict the sign of the entropy change. Is it going to higher Is it going to higher entropy or lower energy? Okay, and the first thing is temperature. Okay, increasing the temperature increases the entropy of a system, which makes sense, right? Because when you increase the temperature, we're adding heat. Heat is a form of energy. If we have, let's say, if we have a sample of gas in a container, let's say, for example, if we add heat to that, we're adding energy. We're adding kinetic energy. The molecules are moving faster, okay? And that will increase the entropy. Okay, if the molecules are moving faster, the system becomes more disordered. Okay? So, physical states and phase changes. So, when a more ordered state changes to a less ordered state, there's an increase in entropy, right? So you should know this. Your most ordered state is the solid. Okay, because a solid is rigid, all the atoms are locked into place. Okay, and the next is liquid, which the molecules are still packed pretty closely together, but a liquid is mobile. And then in a gas, the molecules are basically completely separated, right? So going solid to liquid, there's an increase in entropy. And going from liquid to gas, there's a huge increase in entropy because a gas is really disordered. Okay? Third thing is dissolving a solid or liquid. Okay? The entropy of a dissolved solid is usually greater than that of the pure solid. So in other words, when you dissolve up a solid in a liquid, typically the entropy is going to increase, right? And that's because in a solid, you have all the ions are all packed. The ions are all packed together. Ions, molecules, whichever we're talking about, they're all packed together into some kind of lattice. Okay, and that's your solid. Whereas if you have a liquid, once you dissolve it up and you have in a liquid, now you have, dissolves up, you now have these free-floating ions. This is more disordered. This is highly ordered. This is a little bit more disordered. Okay. Now, dissolving a gas is the opposite case. It's going to result in a decrease in entropy. Why? Because a gas is disordered to begin with. In a gas, the molecules are separated. They're separated, they're flying around, they're zipping around, they're bouncing off the sides of their container. And when you dissolve the gas up in a liquid, it actually becomes a little bit more ordered. So there's a decrease in entropy. All right? And then there's the case of molecular complexity. Okay, that when a reaction occurs with a decrease in molecular complexity, increase in the number of particles, there's an increase in entropy. So basically, think about it this way. If you have a small molecule, or if you have a big molecule breaking down into smaller molecules, that's going to be an increase in entropy. Because a group of small molecules is more disordered than one big molecule. Okay? So, let's look at some examples. Okay? So, well, the answers are on the page, but let's explain this. Let's look at each of these reactions. Does this lead to an increase or a decrease in entropy? Okay. So here we have sulfur dioxide burning an oxygen to form sulfur trioxide. Well, let's look at this. We have 3 moles of gas We have three, it's all gases, so we don't have to worry about solid, liquid. We're looking strictly at the number of moles involved. But, well, so what do we got? We got 3 moles on the left side and 1 mole, or 2 moles rather, on the right side. So molecular complexity is increasing. We're making a bigger molecule out of 2 smaller molecules, right? So entropy is actually going down. We're becoming more ordered, or we're becoming less disordered. Okay, so this would not be an entropy-driven reaction. Okay, now let's look at this example. Carbon monoxide plus hydrogen makes CH3OH, which you guys probably don't know this, but that's the formula for methanol. Okay, so here we have gases, here we have 2 gases, and here we have a liquid. Okay, well, same thing, right? We're going to go to less disorder. Because, well, not only are we making a bigger molecule out of smaller ones, we're also making a liquid molecule out of 2 gaseous molecules. So again, delta S is going to be negative. Okay. Okay, let's look at this example. So what are we doing here? Here we have calcium hydroxide, solid, and we're basically dissolving it up in water, right? So that we go to calcium ions and hydroxide ions. So delta S is going to be positive. Now we're going to an increase in entropy, right? This is the case of a dissolving of a solid. Okay, so here we have a solid, ions that are packed together in a nice crystalline lattice. We're dissolving it up in water. Now we have these free-floating ions in solution. So we're going to a more disordered state. Entropy is increasing. Okay. Here we have another example. 2 nitrogen dioxides make a dinitrogen tetroxide, right? So again, what are we doing? We're making a big molecule out of 2 smaller ones. Big molecule made out of 2 smaller ones, so delta S is negative. We're going to a decrease in entropy. And the last example here is mercury liquid, and the form of liquid is being vaporized to form mercury in the gaseous state. So what are we doing here? We're going from a liquid to a gas. Okay, so we're going to a more disordered phase, right? Liquid to gas is an increase in entropy. All right. So we said a little bit here, a little bit of introduction to thermodynamics, what's entropy, how you can predict, look at a reaction and predict whether it's going to increase or decrease in entropy. And we'll stop here for our first video.